Hello, my lovely biology students. I'm going to help you a little bit with Hardy Weinberg, okay? Because it's a really difficult topic. So, I'm going to break it down. We're first going to talk about allele frequencies, okay? So, in a population, there are only ever two possible allele variations, right? You can either have the dominant allele or what's the other type? That's right, the recessive allele. Those are the only two types of alleles you can have. So some Hardy Weinberg questions will ask you about allele frequencies, okay? And they're only talking about the dominant allele or the recessive allele. In Hardy Weinberg, P, the letter P, is always representing the dominant allele, and the letter Q is always representing the recessive allele. So in allele frequency questions, we are working with a specific formula. Okay? All the P's, right, all the dominant alleles, and all of the recessive alleles, those Q's, they make up all of the alleles in the population. So they make up 100% of the alleles. Correct? So Hardy Weinberg put that into a little formula. Their formula was P, right, plus Q. Those P alleles plus the Q alleles all have to equal 100%. And we can work in percentages or we can work in just numbers and not just numbers, but 100% is the same as saying 1, right? Because to convert a percentage to a number, you just move the decimal over 2 places to the left. So it's the same thing. It means the same thing. I don't want to mess anyone up there. Okay, P plus Q equals 1. And here's another little bit of insight from Miss Passarelli. If you're confused and you don't understand it, write it down and memorize it. Start there, okay? Okay, so here's a question. If, let's say, you get a question that says the frequency of the dominant B allele in a population is 30%. What is the frequency of the recessive B allele, that little b, right? Now we have this equation, P plus Q equals 1. So we're going to try to use that to solve this question. Do we have what P equals? P equals the dominant allele, right? That capital B. And do we know what that frequency is? Yes, it's said in the problem that capital B is in the population and has a frequency of 30%. So we're going to write that as 0.3. Right? Again, here we go. The decimal is there. We're going to move it over 2 to the left. Means it goes right there, 0.3. That's how we convert. Just refresher course. Okay, so we know that. Now what about Q? We don't know what that is. We're solving for that. But we have this handy dandy little equation, right? P plus Q. Oh, we don't know. We're solving for it. Yes, I already said it. But we have this handy dandy equation, P plus Q equals 1. So let's plug in what we have. P is 0.3. We don't know what Q is, and that equals 1. So now let's solve for Q. Q must be 0.7 because 0.3 plus 0.7 equals 1. So Q equals 7. Okay? Those are some simple ways to solve an allele frequency, simply an allele frequency. All right. Let's do another one. If the frequency of a recessive D allele in a population is 40%, what is the frequency of the dominant D allele? All right, so P equals. Do we know what P equals? Do we know what that dominant D allele frequency is? We do not. Do we know what? We do not. Do we know what Q equals? That recessive D allele in the population? We do, because the problem said it's 40%. So we write 0.4, remember? 2 to the left. And now we punch it into our allele frequency equation, right? We don't know P, but we do know Q, and we know P plus Q equals 1. So 1 minus 0.4 equals 0.6, so P must be 0.6. So we've solved for both of our allele frequencies. Okay, now we're going to kick it up a notch, because now we're going to try to determine genotype frequencies, right? 2 alleles in a genotype. Remember, Miss Passarelli, you taught us that in genetics. Yes, I did. Yes, I did teach you that in genetics. We're all bringing that genetics information into our evolution information. All right, so here we have a beautiful, what's it going to be? What's it going to be? Oh, I don't know. It's going to be a beautiful brown eye. Let me speed it along. And over on this side, we have a beautiful blue eye. Okay. So, in our population of human beings, we have different, we have 2 alleles, right, that will represent brown eyes. I'm not saying this properly. We have specific genotypes that will give you brown eyes or blue eyes, right? Brown is the dominant eye color, and a blue is, or light, all light color eyes, are the recessive eye color. Now, you can have 2 genotypes if you have the dominant eye color. So one genotype, you could be homozygous dominant, right? You could be homozygous dominant. So what would your genotype, what would we write for that if we're going to use the letter B? How many capital B's do we have? We got 2 of them. We got 2 capital B's. That's homozygous dominant. Oh my gosh, I forgot the G in homozygous. You guys notice that? Anyone? I didn't spell that right. Cool. Miss Passarelli strikes again. Okay, I just used B. You could use any 2 capital letters you want to use, but I used B, okay? What is the other type of genotype that this person could have if they have dominant eye color? They could also be heterozygous. Oh, I remembered the G that time. Good for me. So, what if you're heterozygous for brown eyes, what's your genotype then? You have a capital allele and you have a lowercase allele, right? Those are the 2 genotypes for dominant eye color. If you have recessive eye color, you only have 1 possible genotype. And that is, dun, 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 you all should be saying it to yourselves right now, little b, Miss P. That is the only possibility if you have the recessive eye color trait. All right. So now how can we figure out the frequency of, let's say, homozygous dominant individuals in a population? How do we do that? How do we figure out the genotype frequency of heterozygous individuals in a population? And I will ask you questions about this. How do we figure out the frequency of homozygous recessive individuals in a population? Because when I'm asking, or anyone is asking these questions, homozygous recessive or heterozygous or homozygous dominant. They're talking about the full genotype. It's not an allele frequency, it's a genotype frequency. Okay? So we need a different formula for tackling it. Okay, so we use the Hardy Weinberg equation that is P squared. I was going to say P cubed. No, P squared plus 2PQ plus Q squared equals 1. Write it down, memorize it. And somewhere on your notes, write genotype frequency equation, because the other equation was for allele frequency. Okay? So P2, and I've color-coded it here for you, but P2, notice it's in pink. So what do you think that P2 represents in this equation? It represents the homozygous dominant genotype. Okay? What do you think the Q2 represents in this Hardy Weinberg equation? I bet you'll never guess it. Yes, I did color code this one too. It represents the homozygous recessive genotype. So what does that leave? What genotype have we not accounted for yet? Well, Ms. Passarelli, you haven't accounted for the heterozygous genotype, and that's what the 2PQ is. Because heterozygotes have a dominant allele and a recessive allele. And in the formula, it's times 2. So let's apply this formula right now. Write it down and memorize it if you have to. I don't care that you fully understand it at the moment. I care that you can apply it. Okay? So here's our formula. I'll keep it up there for us so we can have a nice little reference for it. Okay? And here's our question. What is the frequency of the B allele if the homozygous recessive frequency is 10%? Okay? So homozygous recessive, that's a genotype. So now we know that we're dealing with this bigger formula first. So we know that we're talking about a B allele. We know that it's recessive. And we know that recessive alleles are Q, right? We already learned that. We also know that Q2 stands for the homozygous recessive genotype. Okay? So we know that. And we know that homozygous recessive in this problem equaled 10%. So that's what we know. I look at every question like a detective, like you're walking into a crime scene. Well, what do we got? What do we know? Give me the information. And all questions isolate what you know, what they give you, and write it down. Don't try to keep it all in your head because it gets all jumbled up. Jumbled? Did I say jumbled? Jumbled up. So write it down. All right. So if Q2 equals homozygous recessive, and homozygous recessive equals 0.10, but 0.1, that must mean that Q2 equals 0.1, correct? This is just equalities here. So now we know what Q2 is, so we can solve for Q. And this is when you are going to be using those math skills. How do I go from a squared number? Because I need to figure out just Q. And how do I do that? And it's not division, because this isn't multiplication and division. This is exponents. And so how do I reduce that exponent? I take a square root of it. Okay? So I square root the Q squared, to get Q. But whatever you do to one side, you have to do to the other, because it's like being on a teeter-totter. You got to keep it all even. So the square root of 0.1 is 0.32. So the frequency of the B allele is 0.32. And now you could take that and plug that into this equation if you needed to. And that way you could find P, because it's just P plus 0.32 equals 1. See how it works? Oh, math. Math is wonderful. Math is wonderful. Okay, let's do another one, shall we? Again, I'm giving you the whole equazione. So what is the frequency of the R allele if the homozygous recessive frequency is 15%? Okay, so we know that Q2 is 15%. We know that Q then is square rooted 0.39%. Okay? It's getting easier, isn't it? It's getting easier. It just takes practice. Like everything, man, it just takes practice. Okay. So let's do another one. What is the homozygous dominant frequency? So that's a genotype frequency, right? If the recessive allele frequency is 25%. So notice we don't say recessive genotype frequency. The recessive allele frequency is 25%. Okay? So Q equals what? The recessive allele frequency. And that is 25%. So now how am I going to go from Q to Q squared? How's that going to happen? Or, wait, I don't even need to go to Q squared, do I? I don't. How can I get to the P? What do I know that will, if I have Q, I can get to the P? And if I get to that P, I can get to the P squared, right? So how can we get to that P info? Well, what we already know is that P plus Q equals 1. So if I plug in for Q, I can get P. Now, this is just P, right? This is not P squared. So how do I square this P? Well, P, where is it? P squared equals P times P, right? So P squared equals P times P. So 0.75 times 0.75 equals, bum-ba-da-bum, 0.56. Because we had to square each side. Squared, squared. Okay, so we're employing some math skills here. Let's do one final one. We have homozygous dominant. Giving you the formula again. All right, so it's going to be a little more difficult, but not too much. What is the heterozygous frequency if the recessive allele frequency is 25%? So we have Q equals 0.25%. Again, we need to get to that P info. So P is 75%, right? But now we need to go from there to heterozygous. So for heterozygous, all we need is a P and a Q. Now, do we have that already? Have we already solved for the P and the Q? We certainly have. So let's just plug it in, shall we? Let's just plug it in. So the heterozygous frequency is 0.38. Okay? All right. Oh my gosh, let's do just one more. Why not? Why wouldn't we? So, I'm kind of throwing you a different way of asking it this time. All right, if 98 out of 200 in a population were recessive, what percent is heterozygous? So if 98 out of 200 are recessive, what does that mean? It means that our Q2, because that's our homozygous recessive population, right, is 98 out of 200 or 0.49. So we have our Q2 already. Now what do we need? Because heterozygous is a P and a Q, not squared, right? So we need, frequency of homozygous recessive in population, true. So how do we go from Q squared to Q? Do we remember? You got to square root it. So it's 0.7. Now we have to figure out P. And I bet you already have processed this. You're like, Ms. Pazzarelli, use that P plus Q formula. Easy peasy lemon squeeze. So plug in for Q equals 1. P must equal 0.3. So now we've got Q, we've got P. We can solve for the heterozygous individuals in this population. Do we have everything we need to solve it? Yes, we do. Let's solve it. So 2 times P times Q, plug in what we know, and it's 0.42. Okay? And one thing I would like to say is that one of the reasons that we often, the only thing you can be sure of in a population, and I'm going to take you back to the screen so you can see it. The only thing you can ever be 100% sure of in a population is if someone says homozygous, these people are homozygous for this homozygous recessive, I know that they have 2 lowercase alleles. That's the only genotype that I know for a fact. So when we do Hardy Weinberg, we're often starting from the homozygous recessive standpoint because that's the only one you know. If someone has the dominant trait, we don't know what their genotype is. There's 2 different options. So you can't just say, well, if homozygous recessive is 70%, then homozygous dominant must be 30. You can't say that because there are 2 genotypes here. Okay? Alrighty, Roo. I'm here if you need me.